Welcome students to the MOOCs lecture series on advanced probability theory. This is lecture number 27. As I said at the end of the last class that today we will start law of large numbers. In fact, there is not one law, rather several laws are there we shall look at some of them in detail. Now, law of large numbers is very important from probability theory, particularly in the event of a large number of trials of the same experiment. For illustration, consider tossing a coin n times, and suppose we count the number of heads obtained till in tosses. Say for example, we have number of tosses, say 1, 2, 3, 4, 5, 6, 7, 8, and suppose the outcomes are like this. Suppose the outcomes are head, head, tail, tail, head, tail, tail, tail. Let us go 2 more steps. Head, tail. Then the number of heads, if we count till nth toss, going to be 1, 2, 2, 2, 3, 3, 3, 3, 4, 4. So, if we consider average number of tosses, or then this is going to be 1, 1, 2 by 3, half, 3 by 5, half, 3 by 7, 3 by 8, 4 by 9 and 4 by 10. We know that we obtain the probability P of success, that is head, by dividing the total number of heads by n. This is because the number of heads till nth toss follow binomial with n p, where p is the probability of success. Therefore, if we go back to the experiment just described, if we go back to the experiment just described, we see that the number of or the proportion of heads is changing with the number of tosses. But we know that from the theory of probability, that if a trial can be carried out infinitely number of times, then the number of favorable events divided by total number of events gives the probability of the event. In this case, the event is occurrence of head, therefore, its probability that is P can be obtained by tossing the coin infinite number of times. But in reality, we cannot toss infinite number of times. And therefore, we are never sure what the actual value of P is, and if we toss only a small number of times, then we get different values for P, after each toss. The law of large numbers says that, in essence, says that the average of the results obtained from a large number of trials should be very close to the expected value. Or in essence, that is, if we toss a coin a large number of times, if we toss a coin a large number of times, the average number of heads will be very close to the expected proportion of heads. That is, if S n is equal to x 1 plus x 2 plus x n, where each x I is a Bernoulli random variable, then after a large number of trials, S n by n, the average number of heads will be very close to the average proportion of heads will be very close to the actual proportion of head, that is p. This is true not only for Bernoulli random variable, but for a wide range of cases, as we see below. Now, the above is very important for statistical experiments. However, it has some theoretical limitations. Such as say Cauchy distribution. We know that its expectation does not exist. Similarly, say Pareto distribution, which is of the form alpha x naught to the power alpha upon x to the power alpha plus 1 for x belonging to x naught comma infinity and alpha is greater than 0. For alpha less than 1, the expectation does not converge. Because this 1 will be cancelled when we multiply with x, therefore, this series will not converge. But despite this theoretical limitations, law of large numbers has huge importance in probability. One of the earliest version of this is called Bernoulli's law of large numbers. Which goes as follows. So, Bernoulli's law of large numbers which states that let there be n trials of a random variable that takes only two values, success and failure. Let x be the number of success after n trials. Then probability modulus of x n minus p less than epsilon goes in probability to 1 as n goes to infinity, or alternatively probability modulus of x by n minus p greater than epsilon goes to 0 as n goes to infinity. So, let us analyze the statement. X by n is the proportion of success in n trials and p is the expected proportion. So, Bernoulli's law suggests that the difference between them being greater than some epsilon will probabilistically will go to 0, where epsilon can be any positive quantity greater than 0. Proof. The proof comes from Chebyshev's inequality. which if you remember, which I hope you remember, but let us still recollect that if which states that if z is a random variable with expected value of z is equal to mu, then probability modulus of z minus mu less than epsilon is greater than 1 minus variance of z upon epsilon square. This we have proved earlier. Now, let us apply the above result, the above inequality for x by n. We know x is distributed as binomial n comma p. Therefore, expected value of x by n is equal to n p by n is equal to p, and variance of x by n is equal to n p q upon n square is equal to p q upon n. Therefore, probability modulus of x by n minus p less than epsilon is greater than 1 minus p q by n epsilon square, which is greater than 1 minus 1 by 4 n epsilon square, since the maximum value for p q is equal to 1 by 4. Therefore, for any fixed epsilon, probability modulus of x by n minus p less than epsilon is greater than 1 minus 1 upon 4 n epsilon square, and this part going to 0 as n goes to infinity. That is, x by n converges to p in probability. So, that is the proof that is the proof of Bernoulli's theorem. A more generalized version is called weak law of large numbers, which we shall write as WLLN, and it is stated as follows: let x1, x2, xn be any sequence of random variables such that xi has the expectation mu y less than infinity and the variance is equal to sigma square I. Then the probability that modulus of sigma xi I is equal to 1 to n upon n minus sigma mu I is equal to 1 to n upon n less than epsilon is greater than 1 minus eta for all n greater than equal to n naught where n naught depends upon the particular choice of epsilon and eta, however small positive quantity they are. So, you understand that this is a much stronger statement. We are looking at a sequence of random variables. We are not talking about whether they are independent. We are not talking about whether they are identically distributed. Only thing that if each one of them has a finite mean and a finite variance, then the average of values of the random variables minus the average of their expectations will be very close, that means less than epsilon with a very high probability. Provided variance of sigma xi I is equal to 1 to n is finite and variance of sigma xi upon n square goes to 0 as n goes to infinity. So, this is a very important assumption for weak law of large numbers, as we will see some examples later that this is very, very important. Proof. Again, using Chebyshev's inequality, probability modulus of sigma xi I is equal to 1 to n divided by n minus sigma expected value of xi I is equal to 1 to n divided by n, this less than epsilon is going to be greater than 1 minus variance of, or maybe greater than equal to 1 minus variance of sigma xi I is equal to 1 to n divided by n divided by epsilon square. That is, probability modulus of x bar minus mu bar less than epsilon is greater than equal to 1 minus variance of sigma xi upon n square epsilon square, where x bar is equal to sigma xi I is equal to 1 to n divided by n and mu bar is equal to sigma mu I is equal to 1 to n divided by n. Therefore, we get probability modulus of x bar minus mu bar less than epsilon is greater than equal to 1 minus summation sigma I square I is equal to 1 to n upon n square epsilon square. Now, the given condition is that variance of sigma xi upon n square goes to 0. Therefore, for a given epsilon, this quantity goes to 0. That is, there exists n naught such that for all n greater than equal to n naught, summation of sigma I square upon n square epsilon square is less than eta, however small eta is. Therefore, we see that probability modulus of sigma xi I is equal to 1 to n upon n minus sigma mu I is equal to 1 to n upon n, that probability less than epsilon is greater than equal to 1 minus eta for all n greater than equal to n naught. Hence, proved. What happens if xi's are IIDs? In that case, each xi has expectation, each xi has expectation mu I is equal to mu, and variance sigma I square is equal to sigma square. Therefore, variance of sigma xi upon n is equal to n sigma square upon n square is equal to sigma square by n goes to 0 as n goes to infinity. Therefore, weak law of large number holds trivially. So, let me give you some examples. Suppose xi is distributed as root over I with probability half and minus of root over I with probability half. Therefore, expected value of xi is equal to 0 for all I, and variance of xi is equal to expectation of xi square is equal to I. Therefore, variance of sigma xi upon n square is equal to sigma over I is equal to 1 to n upon n square is equal to n into n plus 1 by 2 n square, which converges to half. Since the condition variance of sigma xi upon n square goes to 0 does not hold, therefore, weak law of large number does not hold. Example 2, xi is equal to I to the power alpha with probability half and minus I to the power alpha with probability half. Therefore, as before, expected value of xi is equal to 0 and variance of xi is equal to I to the power 2 alpha. Therefore, sigma variance of xi is equal to sigma I to the power 2 alpha, I is equal to 1 to n is equal to integration 0 to n x to the power 2 alpha dx, which is equal to x to the power 2 alpha plus 1 upon 2 alpha plus 1 from 0 to n is equal to n to the power 2 alpha plus 1 upon 2 alpha plus 1. Therefore, 1 by n square into sigma variance of xi, I am writing is sigma variance of xi, since variance of sigma xi is equal to sigma variance of xi if xi's are independent. And so, in the above setup, xi's are independent, let us assume. Therefore, 1 by n square into sigma variance of xi is equal to n to the power 2 alpha plus 1 upon n square into 2 to the power alpha plus 1, n to the power 2 alpha plus 1 upon n square into 2 alpha plus 1, which will go to 0 if 2 alpha plus 1 is less than 2. That means, this quantity has to be dominated by this quantity, that is alpha is less than half. Hence, no wonder that when alpha is equal to half, weak law of large numbers does not hold. Another example, consider xi following normal 0 1. Since these are IIDs with finite mean and variance, weak law of large number holds. What about this sequence sigma xi square? We know that xi square is distributed as chi square with 1 degree of freedom. Therefore, expected value of xi square is equal to 1 and variance of xi square is equal to lambda upon alpha square is equal to 2. Therefore, sigma variance of xi I is equal to 1 to n is equal to 2n. Therefore, 1 by n square sigma variance of xi I is equal to 1 to n is equal to 2 by n, which goes to 0 as n goes to infinity. Therefore, weak law of large number holds. Another example, suppose xi is equal to normal with mean mu variance sigma square. Let yi is equal to x1 plus x2 up to xi. Does weak law of large numbers hold for the sequence yi? That is the question. Now, each yi is distributed as normal with I mu and variance is equal to I sigma square. Therefore, variance of y1 plus y2 plus yn is equal to sigma square into 1 plus 2 up to n is equal to n into n plus 1 by 2 sigma square. Therefore, 1 by n square into variance of y1 plus y2 plus up to yn is equal to n into n plus 1 by 2 n square into sigma square, which does not go to 0 as n goes to infinity. So, this is the notation to imply that it is not converging to 0. Therefore, weak law of large number does not hold. Let me now state a very important theorem which states as follows: let x n be a sequence, let x n be any sequence of random variables, let y n be S n minus expected value of S n divided by n, where S n is equal to x 1 plus x 2 up to x n. Then a necessary and sufficient condition for weak law of large numbers to hold for x I is that expected value of y n square upon 1 plus y n square goes to 0 as n goes to infinity. So, this is a very important result and it is a necessary and sufficient condition for weak law of large numbers to hold. Now, let us analyze the result. Y n is equal to the partial sum x 1 up to x n minus its expectation divided by n. Therefore, its expectation is going to 0 means expected value of y n square is becoming very, very small. So, that is the implication. In such a case, x n is going to obey weak law of large numbers. Proof: suppose expected value of y n square upon 1 plus y n square goes to 0 as n goes to infinity. We want to show that x I satisfies weak law of large numbers. That is, given epsilon greater than 0, there exists n such that for all n greater than n, probability modulus of sigma x I upon n minus sigma mu I upon n greater than epsilon, that probability will go to 0 as n goes to infinity. Consider the event A is equal to modulus of y n is greater than epsilon. Therefore, probability of A is equal to probability modulus of y n greater than epsilon. Note that on A, y n square is greater than epsilon square. Now, we know that given A greater than B, A plus A B is greater than B plus A B. That is, A into 1 plus B is greater than B into 1 plus A. That is, A upon 1 plus A is greater than B upon 1 plus B. We want to apply the same result here. So, we have y n square is greater than epsilon square on A. Therefore, on A, y n square upon 1 plus y n square is greater than epsilon square upon 1 plus epsilon square. Let B be the event y n square upon 1 plus y n square is greater than epsilon square upon 1 plus epsilon square. Therefore, probability of A is less than equal to probability of B, because this is contained in this event. Therefore, probability of A is less than equal to probability y n square upon 1 plus y n square greater than epsilon square upon 1 plus epsilon square, that is probability y n square into 1 plus epsilon square upon 1 plus y n square into epsilon square is greater than 1. Therefore, by using Markov inequality, which we have done several classes back, we can write it as this probability is less than equal to expected value of y n square into 1 plus epsilon square upon 1 plus y n square into epsilon square, because the threshold there is 1. Now, it is given that y n square upon 1 plus y n square is going to 0 as n goes to infinity. Therefore, expected value of y n square upon 1 plus y n square goes to 0, implies probability of A is going to 0, implies probability modulus of y n greater than epsilon is going to 0, that is y n converges to 0 in probability. That is, expected value of Sn minus expected value of Sn divided by n converges in probability to 0. Therefore, weak law of large number holds. Okay friends, I stop here today. We have just proved the theorem in one direction. We shall look at the other side, that given that x n holds weak law of large numbers, we shall show that expected value of y n square upon 1 plus y n square goes to 0. Also, we shall do some more examples and some theorems in the next class. Okay friends, thank you.